हाय एवरीवन, वेलकम टू माय यूट्यूब चैनल मैथ स्कूलर। आज का टॉपिक है ग्रुप थ्योरी। उससे पहले मैं कुछ चीज बोलना चाहता हूँ। बहुत सारे बच्चे सपने देखते हैं बीएससी में आईआईटी एग्जाम देने की, बट वो लोग भूल जाते हैं जे बेसिक को क्लियर करना है। इसके बाद आईआईटी में जाने के बाद बहुत सारे दिक्कत, बहुत सारे प्रॉब्लम को फेस करना पड़ता है। मैं खुद आईआईटी कानपुर में एमएससी कर रहा हूँ, मुझे एक्सपीरियंस है। इसलिए मैं तुम्हें बोलना चाहता हूँ, जैम के साथ तुम्हें बेसिक बहुत अच्छे से तैयारी करनी पड़ेगी, नहीं तो बाद में बहुत प्रॉब्लम फेस करना पड़ेगा। इसलिए मैं मेरे से जितना हो पाए, मेरे जितना एक्सपीरियंस है तुम्हें देने की कोशिश करूंगा, अच्छे से समझाने की कोशिश करूंगा। तुम लोग सपोर्ट करना। सो व्हाट इज द डेफिनेशंस ऑफ ग्रुप थ्योरी? A group is an ordered pair, G star, where G is a non-empty set, and star is the binary operations on G such that the following properties hold. What is the property? One is the associative law. For all A, B, C belongs to G, A star, B star, C equal to A star B, A star C. Second property is existence of an identity. There exists E belongs to G such that A star equal to A star A for all A belongs to G. And third is existence of an inverse. For all A belongs to G, there exists B belongs to G such that A star B equal to E equal to B star A. क्लियर? एंड कुछ कुछ बुक में यहाँ पर और एक कंडीशन होती है, वो क्लोज प्रॉपर्टी। व्हाट इज द क्लोज प्रॉपर्टी? इफ A एंड B belongs to G, then A star B also a member of G. And these four conditions, if G satisfies these four conditions, then G is called group under a star. Under what is operations? What is binary operations? A star operations. Clear? So, what is the definitions of commutative group or an abelian group? A group G star is said to be, first, it is a group, and second, it is said to be abelian if A star B equal to B star A for all A B belongs to G. What is the theorem? Theorem 1. Prove that in a group G star the inverse of each element is unique. So, let A belongs to G. Suppose B and C are both inverse of A. By definitions of inverse, I can write A star B equal to B star A equal to identity and A star C equal to C star A equal to identity. Where is the identity element of the group G? Now, I can write B equal to B star E, and E I can write A star C. So, by associative property of A star, B star A equal to E, A star C equal to C. So, B equal to C. So, first we consider two inverse of A, and at the end I show that B equal to C. This proves the uniqueness of the inverse. Similar proof we discussed in the first class. What is the question? The inverse of identity element is unique if it exists, and for the group inverse always exists. So I can prove similar way the identity element of the group is unique. Clear? Next theorem, cancellations law. In a group G star, for all ABC belongs to G. On the left cancellations law, A star B equal to A star C implies B equal to C. And right cancellation law, B star A equal to C star A, then B equal to C. Proof on. Since G is a group, the inverse of A exists by definitions of group. And what is the question? A star B equal, if A star B equal to A star C, then B equal to C. So it is our given conditions. Now, if I multiply both sides from the left side inverse, then I can write A inverse A star B equal to A inverse A star C. Now, since A star is associative, so I can write A inverse A star B equal to A inverse A star C. A inverse A star A equal to identity by the definitions of the group. Hence, A star B equal to A star C. And so B equal to C. Similarly, I can prove the theorem 2. Here we multiply A inverse from the right hand side. In, in this case, it is called the right cancellation law. प्रूफ करने से पहले पहले क्या बोलना चाहती है क्वेश्चन में उसको समझने की जरूरत है, नहीं तो रट के कुछ प्रूफ नहीं होगा। ठीक है, नेक्स्ट पेज। थियरम 3, prove that in a group G star, the inverse of the product of two elements is the product of their inverse taken in the reverse order. That is, A star B inverse equal to B inverse A star A inverse for all AB belongs to G. Here we want to prove that the inverse of A star B is B inverse A star A inverse. कोई भी एक एलिमेंट A belongs to G, then A dash is said to be inverse of G if A compose A star A dash equal to A dash compose A equal to identity. So for this proof, we want to show A star B, A star B inverse A star A inverse equal to identity, and B inverse A star A inverse A star B equal to identity. So first part, A star B inverse A star A inverse equal to, by associative property I can write A star B inverse A star A inverse, and it can be write A star B inverse A star A inverse. Now since B inverse is the inverse of A, so by definitions of group theory I can write B star B inverse equal to identity. Clear? Now A star E equal A star A inverse. So A star E equal to A, and I can write A star A inverse. Similarly, we can show the other side. This proves that a first condition and second conditions imply B inverse A star A inverse is the inverse of A star B. So I can write this, and this complete the proof. Clear? नहीं डाउट बोलना जरूर, नहीं तो डाउट बहुत बड़ी होने के बाद ओ। Now theorem 4. What is the question? Prove that in a group G star, each of the equations A star x equal to B and Y star A equal to B has a unique solutions for all AB belongs to G. So for this theorem, let AB belongs to G. And since G is a group, the inverse A inverse of A exists. Multiplying both sides of A star x equal to B in the left by A inverse, we get A star A inverse A star x equal to A inverse A star B. And by associativity, A inverse A star x equal to A inverse A star B. And so we get x equal to A inverse A star B. So we get the solutions of the equations A star x equal to B. Next page. Now we want to prove that the uniqueness of the solution. So for this, we consider two solutions of the equation A star x equal to B. Let x1 and x2 are two solutions. Then since x1 x2 are two solutions, so it satisfies the equations, we know that, and A star x1 equal to B and similarly A star x2 equal to B. So by cancellation law, I can write x1 equal to x2. We consider two solutions, then we see that the solutions are same. This proves that the solution is unique. Similarly, we can solve y star A equal to B equations. Next theorem. Theorem 5. A semigroup G star is a group if and only if the following conditions are satisfied. What is the first conditions? There exists E belongs to G such that A star A equal to A for all A belongs to G. And second conditions, for all A belongs to G, there exists B belongs to G such that B star A equal to identity. Now, what is the definitions of semigroup? We discussed in the first class. कोई भी मैथमेटिकल सिस्टम जी स्टार को सेमीग्रुप बोल सकते हैं तब अगर स्टार इज एसोसिएटिव. Clear? Here, if you notice, you can see first conditions is the left side of identity, existence of identity, and second condition is the existence of left side of existence of inverse. So, for proof G star is a group, we want to prove the right hand side of existence of identity and existence of inverse. So first we consider that G star is a semigroup satisfying the conditions 1 and 2 and let A belongs to G, and the by conditions 2 we can there exists B belongs to G such that B star A equal to identity. Clear? Again by 2, since B is a member of G, similarly I can write there exists a C belongs to G such that C star B equal to E. Now I can write A equal to E star A by the property of conditions 1, and equal to C star B star A equal to C star B star A equal to C star A. Now A star B equal to C star E star B. Here A means C star E we already find, and by associative property C star E star B equal to C star B equal to E. So first we show that B star A equal to E, and second we find that A star B equal to E. So A star B equal to E equal to B star A. This proves that B is the inverse of A. Now the right side we मैंने प्रूव कर लिया existence of identity का, inverse का. Now we want to prove the right side of existence of identity. For this we let A star equal to A star B star A equal to A star B star A, since A star is associative. Now I can write A star A equal to A. So A star A equal to A. Clear? Now next page. Hence A star equal to E star A equal to for all A belongs to G implies that E is the identity element of G. This proves that E is the identity element of G. Now here G star is a semigroup, and we see that for each element A belongs to G, there exists B belongs to G such that A star B equal to E equal to B star A. That's mean for each element of G has the inverse in G and is the identity element. So by the definitions of group theory, G star is a group. And for conversely portions, if I consider G star is a group, then obviously G star is a semigroup, and 1 and 2 conditions it is holds. Clear? Next. Now last theorem. What is the theorem? A semigroup G star is a group if and only if for all AB belongs to G, the equations A star x equal to B and Y star A equal to B have solutions in G for x and y. Here for all AB belongs to G. Here do not mention what is the nature of AB, any arbitrary element of G. So suppose that the given equations have solutions in G, let A belongs to G, then Y star A equal to A has the solutions. I can write because here for all AB belongs to G. Let the solutions be U, then U star A equal to A. Let B be any arbitrary element of G. Consider the equations A star x equal to B. Then by the given conditions it has also a solution, say C. Then A star C equal to B, because Every solution satisfied the equations. Now U star B equal to U star A star C, because B equal to A star C. And by associative property, I can write U star A star C, and U star A mean A, so it can be write A star C and equal to B, because U star A equal to A. Since B was the arbitrary element of G, we have U star B equal to B for all B belongs to G. So we see that from this, U star B equal to B for all B belongs to G. So use the left identity in G, and hence G plus G star satisfies the conditions on of previous theorem. In previous theorem, we can see that a semigroup G star is a group if and only if the first conditions is there exist E belongs to G such that A star E equal to A for all A belongs to G, and second conditions for all A belongs to G there exist B belongs to G such that A star B equal to E. Here the first conditions satisfied, and the second conditions. Now for the second conditions, next consider the equations Y star A equal to U. By assumptions, the equations has a solution, say D. D belongs to G. Sorry, it is wrong. D belongs to G होगा यहाँ पर. B such that D star A equal to U, and thus the conditions 2 of the theorem 5 is satisfied. Clear? Therefore, by theorem 5, G star is a group. By theorem 5. And the conversely question is obvious, because if it is group, then the equations has the solutions we already discussed in class. Clear? It is an interesting problem. Example on. What is the questions? And show that M to R, the set of all 2 cross 2 matrix with real entries, forms a commutative group under matrix additions. सो ग्रुप प्रूफ करने के लिए हमें 4 प्रॉपर्टी को सेटिस्फाई करना पड़ेगा. पहली प्रॉपर्टी क्लोजर प्रॉपर्टी, सेकंड एसोसिएटिविटी, थर्ड आइडेंटिटी, एंड फोर्थ इनवर्स, मानी ईच एलिमेंट हैज इनवर्स. इसको हमें शो करना पड़ेगा. पहले क्लोज प्रॉपर्टी, लेट ए बी बिलोंग्स टू एम टू आर, देन ए प्लस बी is also 2 cross 2 real matrix, because sum of 2 cross 2 real matrix is also 2 cross 2 real matrix. Hence M to R is closed under matrix additions. Associativity, for all ABC belongs to M to R, A plus B plus C equal to A plus B plus C. Matrix additions is always associative. If you want, you can check, consider a matrix is A1 A2 B1 B2 B matrix is, ऐसे करके तुम 3 मैट्रिक्स कंसिडर करके देखना, वो कम्यूटेटिव होगा, एसोसिएटिव होगा. आइडेंटिटी, the zero matrix O2 satisfies A plus O2 equal to O2 plus A equal to A for all A belongs to M to R. So O2 is the identity element, and inverse, for A belongs to M to R, minus A matrix satisfies A plus minus A equal to minus A plus A equal to O2. Therefore minus A is the inverse of A. And commutativity, for all AB belongs to M to R, A plus B equal to B plus A. It is obvious. If you want, it can be checked easily. Consider A equal to A1 on, A1 to, A2 on, A2 to, and B is B1 on, B2 to, B2 on. ऐसे करके कोई भी एक मैट्रिक्स कंसिडर कर लेना, 2 मैट्रिक्स देखना, वो कम्यूटेटिव होगा. Clear? So M to R is an abelian group. Clear? Next problem. Next question. It is a very important question. What is the question? Let X be a non-empty set. Let G be the set of all functions f such that x to x Define a binary operations circle on G by compositions of functions. Here, binary operations is compositions of functions. Show that it is a semi-group with identity but not a group. So, first we prove that it is semi-group. For this, we want to show that the circle, that means the compositions of functions, is closed and it is associative. Since the compositions of two functions from x to x is again a functions from x to x, the operations circle is closed on x, on G. It is obvious portions. And compositions of functions is associative. It is obvious, you can check easily. Identity element. Define a functions I such that x to x by I of x equal to x for all x belongs to x. Then for every f belongs to G, f compose I compose f equal to f. So I can say I is the identity element of G compositions and hence G compositions is a semigroup with identity. Clear this problem? It is so easy, but क्वेश्चन को देख के थोड़ी डिफिकल्टी लग सकता है. For the second part, for proving G compositions is not a group, we give a counter example. Let X the set A comma B, define F and G functions belongs to G by f of A equal to A and f of B equal to A. G of A equal to B, G of B equal to B. Now we see that f compose G of X equal to f of G of X equal to A for all x belongs to x, and f compose H of X equal to f of H of X equal to A for all x belongs to x. Hence we see that f compose G equal to f compose H. If G compositions is a group, then f compose G equal to f compose H imply G equal to H, but here G not equal to H. So the cancellations law do not hold in G, hence G compositions is not a group. Clear? Next problem. Example 3. Let G star be a group if G contains exactly two elements, then G is commutative. Since G has only two elements, one of them must be identity because by the definitions of group, G contains a identity element. Let G equal to E, comma A. E is the identity element and A not equal to E. Since G contains exactly two elements, hence A not equal to E. Because G is a group and every element has an inverse, so A inverse exists. The inverse of A must belongs to G, but A inverse not equal to E. If A inverse equal to E, then A equal to E. So A inverse equal to A. Only possible of A inverse is A. Hence A star A equal to E. So the only possibles of product are E star equal to E. It is obvious because E is the identity element and E star equal to A, A star equal to A. This three happens because E is the identity element. And the last happened because we already proved A star A equal to E. This shows that X star Y equal to Y star X for all XY belongs to G. Clear? Because A star A equal to E equal to A star A and A star E equal to A, which is equal E star A. So here all the possibilities shows that X star Y equal to Y star X for all XY belongs to G. Clear? Next and last problem. What is the question? Let G multiplications be a group if every element of G is the inverse of itself, then G is commutative or abelian. Here every element of G is the inverse of itself, that is A inverse equal to A for all A belongs to G. And for this proof, let AB be any arbitrary element of G. Consider the product A into B, and by the first theorem, A into B inverse equal to B inverse into A inverse. And by the conditions of these questions, I can write B inverse equal to B and A inverse equal to A. But since G into multiplications is a group and AB belongs to G, so A into B belongs to G, and by the given conditions, A into B inverse equal to A into B. So we can write this, and A into B inverse mean B into A. Since this is holds for all AB belongs to G, so the group is abelian. थैंक यू। अगर कोई डाउट होगा तो पूछना कमेंट बॉक्स में।